All right, let's get started as soon as the projector turns on. Okay, well, I'll start with the class announcements, and this will come up shortly. So homework 4 is due next Wednesday, so hopefully all of you have checked that out, gotten started on it, and we'll be ready to turn it in on time. And also, even though this is a little further away, do keep in mind that the project milestone will actually be due in 2 weeks. So hopefully all of you have incorporated the feedback that we provided you on the project proposal and are making good progress on your final project. So it's really important to make sure that you do get some progress towards completing your final project for the milestone, because the milestone is your opportunity to receive feedback on how your project is going. And that feedback can be really helpful to make sure that your actual final project sort of meets the requirements for the course. So making sure that you have a good milestone report, it's really there for your benefit. It will ensure that you get good feedback on your project. So do make sure to make some progress, write up how things are going for the milestone report. If you want to change the direction of your project from what was in the proposal, that's totally fine. You should make sure you describe that in the milestone report as well, and then that'll also be your opportunity to receive some feedback on your new project direction. So do make sure you take advantage of that. It's really there for your benefit. Okay, today's lecture. Today we're going to talk about exploration, and this will probably be a 2-part lecture, and we'll conclude it on Friday. So we're going to talk about what is exploration, basically what's the exploration problem. We're going to talk about multi-arm bandits and kind of theoretically grounded exploration. So exploration algorithms are actually very difficult to analyze theoretically, and oftentimes we do a lot of our theoretical analysis in highly simplified problems, which are called bandits. And I'll explain why they're called bandits and what these really are. And I'm going to talk about 3 broad classes of exploration methods: optimism-driven exploration algorithms, posterior matching exploration, and information theoretic exploration algorithms. And these are kind of 3 different themes that we'll see both in the world of multi-arm bandits and later on in the setting of deep RL algorithms of the sort that we actually work with in this course. So the goals for today's lecture will be to understand what is the exploration problem, understand how theoretically grounded exploration methods can be derived, and understand how we can do exploration in deep reinforcement learning settings in practice. And this we'll begin talking about this towards the end of today's lecture, and then we'll conclude that discussion with more practical exploration algorithms probably on Friday, depending on how the timing goes. Okay, but let's start with the basics. What's the problem? What is why do we have 2 entire lectures about exploration? What's the exploration problem? Well, let's think back to the Q-Learning Atari games stuff that you guys did for homework 3. Some of you might have tried different Atari games. Hopefully all of you at least tried Pong. This is a different game. This is a game called Breakout. And it's like reasonably easy to learn this game with Q-Learning. So probably if you were to take your homework 3 Q-Learning code and you were to run it on this game, you would probably get a pretty good solution. Maybe it wouldn't be quite as awesome as this video, but it would do something pretty good. So this is mostly easy. This is another game in the Atari suite, and this game is impossible. So if you were to take your homework 3 code and you were to run on this game, you wouldn't get anything good. And if you don't believe me, you can go home and try this. This is a game called Montezuma's Revenge. It's in the same exact Atari learning environment suite that you guys used for homework 3. Just flip the switch, run this thing, and see what it does. I don't think it'll work very well. So why is that? Why is this thing easy and this thing is impossible? Well, let's look at what this game called Montezuma's Revenge actually entails. I'll tell you a little bit about the game because some of you might not be familiar with it. I don't think it's a very good game, actually. Like, I tried playing it. It wasn't really a lot of fun. I like some of the other games better. But here's basically how it works. You control this little guy with a hat. He's kind of like an Indiana Jones type of character. I guess he's like exploring this kind of Mayan pyramid or something, and he starts off at the top of the pyramid and needs to get to the bottom right, I think. And the pyramid is populated by all sorts of interesting creatures, like this rolling skull. And there are some events you can do in the game that will give you some rewards, and you finish the game when you reach the particular room, and that's the conclusion. So here's how the reward function works. You can kind of figure out the dynamics from watching this video. If you pick up that key, you get a reward. So you see your score up here. You get a score of 100 for picking up the key. So one might conclude that grabbing the key is a good thing. If you open the door, you get a reward. I think you get like 1,000 or something for taking this key and opening this door here. If you touch the skull, you die, but of course die is like a human concept. What does die mean in the game? Well, it means that these little icons that show, I guess these are your hats, you lose one hat, and the skull disappears. So, okay, is that like a good thing or a bad thing? A little hard to tell, and then there's no reward for it. So finishing the game kind of only weakly correlates with these rewarding events. So maybe picking up the key is a good idea because you have to get out of this room, but you get a reward whether you go left or right, but those two paths lead you to different rooms. So the reward doesn't really tell you whether you're doing well or poorly. It just kind of provides a little bit of arbitrary stuff along the way. And in fact, a very legitimate strategy here might be that if you're really bad at jumping over the skull, maybe you go and get killed by the skull to make it go away, and then you have an easier time getting the key next time at the cost of one of your hats, I guess. So, all right. Does anyone have any ideas about why this game might prove to be especially difficult for these Q learning algorithms that we implement for Homework 3? Does anyone have any ideas?
The reward is sparse.
The reward is sparse. So if you hear the term sparse reward, what that refers to is it's sort of a bit of jargon that just says most states have a reward of 0, and occasionally you have a reward that is non-zero. And that is difficult because if you mostly have rewards of 0, your Q-learning algorithm isn't really learning anything. So if you imagine the form of the Bellman backup, it's like R plus next Q. If R is almost always 0, you're just telling it make current Q equal to next Q. This game actually has rewards. Like if you pick up the key, you get a reward. If you open the door, you get a reward. So there are it's not like you get no reward at all. It's just that the rewards are not really very strongly correlated with what you're supposed to be doing. So at the end of the game, you finish it and you get a big reward, but the things you have to do along the way are not necessarily the ones that are actually the most rewarding. There's another kind of maybe somewhat philosophical point here, which is that when we look at a video like this, we kind of know what these things mean. We know that keys open doors, and if you're playing a video game, opening a door and going to a different level seems like a good thing because you know something about video games. And there's a little bit of kind of symbolism here, we kind of associate skulls with bad stuff and death. I guess at least most of us do. So we kind of think maybe this is a bad guy, even though we've never touched it before. We might not know that it's bad for sure, but we can guess. And just the basics, you see this guy jumping around, when you push the buttons, you kind of figure out that you're controlling the guy and not the skull, for example. So these are all things that are very apparent to us just because we know how the world works, and the game is meant to kind of mimic our real physical world. So maybe if we want to kind of imagine what this game looks like to the learning algorithm, maybe we can think of a different problem where we can eliminate some of these priors that we have that the algorithm lacks, and think of another example where we sort of put ourselves in the algorithm's shoes, where it's a little easier to appreciate what our Q-learning algorithm is really going through when it tries to play Montezuma's Revenge. So there's this card game, also in my opinion not a very fun card game, but it makes the point, called Mao. Can you raise your hand if you've ever played this game? Okay, so maybe a sixth or an eighth of the room. Not as many of you. So let me tell you a little bit about this game. It's a very peculiar card game. It's as usual, you kind of sit in a circle, and there's one person who is the chairman, hence the name. And the rules of the game are actually very peculiar. So at the beginning, what you're supposed to do is you're supposed to tell every new player, the only rule that you may be told is this one. meaning that like we're not going to tell you any rules. The game has rules. In fact, the chairman should know what the rules are, but you don't know what they are in advance when you start playing. And of course, the rules change every single game. If you've heard of Calvin Ball, similar idea. So that makes for a very peculiar experience. You're playing this game, you're putting down cards or something like that, and occasionally someone will like yell at you for doing the wrong thing. You don't know why, and then you incur a penalty. So if you break a rule without knowing what that rule is, you incur a penalty, you pick up another card, and then maybe you feel a little bit of contrition about this. But over time, as you play the game, you kind of figure out what the rules actually are. So you can discover the rules through trial and error. The rules exist. They're not like completely random. It's not like people will randomly yell at you. It's just that you don't understand the logic about them in advance. You have to figure it out through trial and error, through interaction. So a reinforcement learning algorithm playing the game of Montezuma's Revenge is essentially going through this experience. It's pushing buttons, and randomly it gets either a jolt of electricity or a treat. And it initially doesn't know the logic behind these and has to figure it out as it goes. So the rules don't always make sense to you until you've experienced the rewards or penalties enough times. So these kind of temporally extended tasks like Montezuma's Revenge or Mao become increasingly difficult based on a few factors. First, they become more difficult depending on how temporally extended the task is. Basically, how long do you have to interact with this thing before you figure out whether you've been doing the right thing or not? How little you know about the rules in advance. So reinforcement learning algorithms assume they basically know nothing until they've started interacting with the environment. You can imagine, for example, that your goal in life was to win 50 games of Mao. So you've been doing all these things, you've been coming to class, doing your homework, but actually if you had just gone and played 50 games of Mao, you would win at life, like you'd get millions of dollars or something, whatever your definition of winning at life is. That's a really bizarre world to live in, but if you have no prior about what's going on, this seems just as likely as anything else. So that maybe gives you some idea of what these RL algorithms are really going through when they're trying to solve some of these tasks with temporally delayed rewards. Question?
I think another problem here is that we have 52 factorial, like things you can go through. Like, even if you know what's the reward, the space is so big that you might not really.
Right. So the comment for those of you that didn't hear is that, well, another issue with like card games is that the number of possible states is huge. There are lots of different permutations of what cards you're holding in your hand. So even if you knew something about the goal, it might take you a really long time to understand all the interactions with this large state space. In fact, these problems are kind of isomorphic to each other. So you could easily say that basically any problem where your challenge is unknown rewards, you can construct an equivalent MDP where the reward is known but the problem is still hard. It's very easy to do that. Just add a state variable that is equal to reward. You have a known reward, which is that state variable, but the interactions of that state variable with the rest of the state is unknown. So it's not really about rewards per se. The rewards are just the easiest way to explain it. But in fact, it's about the whole MDP, either transitions or rewards. Okay, here's another example. And this is actually the same problem, but viewed from a slightly different perspective. This problem is difficult not because we don't understand the high-level logic, but because the space is so large. So here's a task where you have a robotic hand that's supposed to pick up objects, and it gets a reward when it gets the object to a particular location. Now the trouble here is that the hand can do all sorts of different things, if it's just randomly wiggling the fingers around. So the chance of just randomly wiggling fingers to produce the desired motion, to reorient the pen or to pick up the object, is very, very low. So here, it actually looks like a very different type of problem, but the challenge is the same, that the kind of naive exploration strategies like the epsilon greedy strategy we had in homework 3 are just so extremely unlikely to do the thing that you're supposed to be doing that you might never figure it out without some additional guidance. Okay, so oftentimes if you see kind of the exploration problem posed in a class or in a talk or a lecture or something, oftentimes people frame it as this kind of dichotomy between exploration and exploitation. And this is actually also the same thing, but it might be a little subtle as to why this is. So there are kind of two potential definitions of the exploration problem that are actually basically the same, but they sound very different at first. So the first one, which is kind of the one that I was insinuating with the discussion of Montezuma's Revenge, is the following. How can an agent discover high reward strategies that require a temporally extended sequence of complex actions that individually are not very rewarding. Meaning you have to do a whole bunch of things. Each of those things doesn't actually give you any reward or any indication that they're the right thing to do. And at the end, having done each of those things in exactly the right way, then you receive some indication that you've succeeded. That's one version, one way to pose the problem. And another way to pose the problem is, how can an agent decide whether to attempt new behaviors or to discover new ones with higher reward? How can an agent decide whether to attempt new behaviors in order to discover ones with higher reward, or continue to do the best thing that it knows so far? And the reason that these things are basically equivalent is that if you have this temporally extended sequence of things you have to do before you receive the reward, the reason you might opt not to do the right temporally extended sequence of things is because there's some other thing you can do in the meantime that is much, much simpler, that locally looks better. So maybe picking up the key in Montezuma's Revenge, it gives you a little bit of reward. If you lose at the game and you reset the environment, the key appears again. So what you could do is you could pick up the key, lose at the game, reset, pick up the key again, and so on. That's not a very good way to win the game, but it's, if you don't know anything else, if you don't know that this other temporally extended sequence of actions might actually be much better, that seems like a local optimum to you. So indeed, these things are actually basically the same. So exploitation here, when someone says it's exploration versus exploitation, exploitation refers to doing what you know will yield the highest reward among the things you've seen so far. And exploration means doing things that you haven't done before in the hope that they will give you higher reward. Of course, there are a lot more ways to explore than there are to exploit in most cases, because most of the things you haven't done yet are probably not actually very good, but there are a few that are. So just a few examples to really solidify this point. These are borrowed from David Silver's slides. Restaurant selection, right? Something you might be faced with in your lives. You could go to your favorite restaurant, which you know will be kind of decent, or you could try to go somewhere new. And probably a lot of the time this will not be as good as your favorite restaurant, but sometimes it might be really good. So, again, there are many more ways to do this than this. Online ad placement, a very practical problem. You could show the most successful advertisement, or the one that your system currently believes is the best match for that user, or you can try to show a completely different advertisement, which most of the time will actually be a really bad choice, but occasionally you might discover a better match for each user. Oil drilling. You could drill at the best known location, or you could drill at a new location. Again, most of the time this will not yield a good outcome, but if you only ever do exploitation, then you might never really discover any kind of high yield locations. Figuring out how to devise algorithms for exploration and proving that those algorithms actually do well in a theoretical sense is very difficult. So a question that we might ask is, well, can we derive an optimal exploration strategy? So if I tell you everything about the MDP and so on, can you write down an exploration strategy that is in some well-defined sense optimal? That's a very difficult question to answer, and in fact, generally it's impossible to answer for very large and complex MDPs of the sort that we deal with in this class, but we can begin to answer that question for extremely simplified decision problems, and that's what we'll do actually in today's lecture. So to begin dealing with this question, well, first we have to answer, what does optimal even mean? And I will actually introduce a definition of optimality for exploration later on. So you might, basically at a high level, you might imagine this is some kind of measure of how much worse is your strategy than some Bayesian optimal strategy that reasons about beliefs. But we'll actually make this concrete and explain what is the Bayes optimal strategy and what does it mean to have regret against that strategy. So more on this later. And then you can put all of the different types of decision-making problems on a kind of continuum between ones that are the most amenable to theoretical analysis for exploration and the ones that are the least amenable or completely intractable. So the most amenable to analysis are what are called multi-arm bandit problems. We'll discuss these more at length, but at a very high level, a multi-arm bandit problem is basically a very degenerate MDP that has exactly one time step and one state. So all you do is you pick an action. A slightly less degenerate decision-making problem is what's called a contextual bandit, which also has one time step, but now it has both a state and an action. So you actually observe something and then choose something. Whereas in the multi-arm bandit, you don't observe anything, you just choose an action. You could do some analysis on small finite MDPs. MDPs where basically solving the MDP is trivial. You just run value iteration and get an answer. There's a little bit of analysis you can do there, but that's already getting into the realm of things where it's getting intractable. And then for the kind of large infinite MDPs with continuous state spaces or exponentially large state spaces, there basically all bets are off. Exploration there cannot be analyzed tractably. What we can do is we can begin over here on the left side of this continuum, derive algorithms that are principled, that have some guarantees about optimality, and then design, inspired by those, design algorithms over here that are kind of based on similar principles that are a little bit more heuristic, but we might have reason to suspect they'll work well because their analogs in this world are can provably work well. So that's basically how we're going to go about designing exploration algorithms for things on this end of the spectrum where analysis is intractable. So what makes exploration problems tractable? Why can we do some analysis in this world? Well, it turns out that in the world of multi-arm bandits and also actually contextual bandits, we can actually formalize the exploration problem itself as a decision-making process. It's kind of a meta-level decision-making process. So your state there is now going to be belief over the model, and your decision is going to be your exploration decision. So it's a meta-level MDP, and we'll see that concretely in a few slides. So that's what makes it tractable to analyze the bandits. And of course, policy learning is trivial even when you start reasoning about beliefs, because the policy, for example, for the multi-arm bandit is to just take the best action. So there's no kind of planning or anything that goes on there. For small finite MDPs, typically if you see kind of theoretical analysis of exploration for small finite MDPs, it has some kind of flavor of Bayesian model identification. And in these small finite MDPs, you can reason about the value of gaining information about the model, and that's how you can do a little bit of analysis there. We won't get into this too much, but that's kind of the general flavor there. And then for larger infinite MDPs, basically the methods to prove optimality don't really apply anymore because the analysis is intractable, but you can take inspiration from optimal methods in kind of these smaller settings and then design analogous algorithms for large tasks, which you might hope will work well because they provably work well over here. So that's the basic kind of strategy we're going to take to develop exploration algorithms. And then usually we put in some hacks to make them actually work, which is what we always do in deep learning. All right, so let's talk about the actual technical details of all this stuff. Let's start with these bandits. So what's a bandit? This is not actually what we mean. Actually, the metaphor for bandit comes from something else. So a bandit is kind of the Drosophila of exploration problems. It's a really, really simple model system that we can analyze tractably that'll let us develop good exploration algorithms. So Drosophila fruit fly, that's what's used in a lot of kind of biology experiments, a basic model system that is a simple representative of more complex systems we might actually care about. So the word bandit doesn't actually refer to this guy, it actually refers to this thing. So it's a little bit of kind of, I guess, American colloquialism. The one-armed bandit refers to a slot machine. Why a slot machine? Well, because a slot machine gives you rewards, but it gives you those rewards stochastically. And perhaps if you go into a sketchy casino that has a poor reputation, you might not know what is the probability that their slot machines will actually give you high rewards. So if you just have one slot machine, you have only one action you can take. You're sort of a compulsive gambler, so you can't choose not to play. So the only action you have is to pull the arm. It's a very simple game. You can only do one thing. And if you pull the arm, then you get a reward. And that reward is randomly distributed. It might be as little as 0, or it might be a little bit higher. I guess you pay some money to play, so it might be negative too. But a much more interesting setting is when you have a number of different options. You have a number of different slot machines. You can pull each of their arms, and maybe some of them might actually be better than others. Maybe one of the slot machines is more likely to give you a reward. And this is the kind of setting that we'll actually analyze. So when you have these multi-armed bandit, this is called a multi-armed bandit. It's not a one-armed bandit, but it has multiple arms. Each arm has some reward. The rewards are randomly distributed. So it's a little different than the MDP setting we're used to. Here, every time you execute this action AN, you might get a different reward, but it comes from some distribution. So maybe action 0 is the best action. It gives you a reward of 1,000,000 with probability 90%, but with probability 10%, it might still give you a low reward. So the best strategy, of course, is to play the arm with the largest expected reward. Because the randomness of that reward, that's something that's out of your control. So the best you can do is pull the one with the highest expected reward. So your reward is distributed according to some probability distribution conditioned on the action you executed. That's our model system. And you can view this as basically an MDP with one time step and no state. So there's no context that you get on which to make your decision. It's always the same arms. All you have to do is pick the action. Yes, question?
Couldn't it be the state, the current state you see the values on the packet?
Yeah, so the question was, well, couldn't you kind of formulate a sort of state which is the current rewards that you've seen? And the answer is that yes, you can, and that's actually how we're going to derive optimal exploration strategies. So I'll discuss that a little bit later. Okay, so you have an unknown per action reward distribution, and the reason this is an exploration problem, of course, is that you don't know these reward distributions in advance. So maybe the best way to understand the multi-arm bandit problem setting is to actually play with them a little bit. So we're going to play with a multi-arm bandit, and the setting is the following. It's a drug prescription problem. So you can kind of imagine that you're a doctor. Your job is to prescribe drugs. That's all you do. I guess you're not a very good doctor. In fact, you're such a bad doctor, you didn't even go to medical school. You don't know how to prescribe the drugs. You have to figure it out on the job. So it's a very difficult kind of doctor problem. So you have 4 drugs. You don't really know what they are. They're just drug 1, drug 2, drug 3, and drug 4. In fact, you don't even know what you're diagnosing. So all you have to do is pick which of these drugs is the best drug. And your reward is 1 if your patient lives, and 0 if your patient dies. So perhaps this is stretching the analogy a little bit, but that's the setup. So patients come in. Since you're not a very good doctor and you didn't go to medical school, you're not actually going to bother to diagnose them. You're just going to give them 1 of the 4 drugs. And we'll just tell you right away that these drugs will have the same effect on every patient. So the good drug will cure every patient. The bad drug will kill every patient. But there's always some randomness. So there's no context about the patient. It's not like you know the one with the fever gets one drug and the one without the fever gets a different one. They all are statistically identical. But the outcomes are a little random. So even the good drug might sometimes not save the patient. So the stakes are high. And the question is, how well can you do? And that's the question we're going to try to answer next. So here's how we're going to play this game. We're going to, since there are a lot of us, we're going to have to vote. So we're not one doctor, we're a whole room full of doctors. So the way that we're going to vote, everyone can see that, right? Yeah, okay. So the way we're going to vote is I want each of you to hold up your hand with a number of fingers corresponding to the number. So if you're on drug 1, you do this. If you're on drug 2, you do that. And I also want you to say the number, because then it's more fun, because then we can hear what everyone is saying. So let's go with the first patient comes in. Which drug do we want? 2. Okay, I think 1 is actually the winner based on looking at the hands. So the patient died from drug 1. Okay, new patient comes in. Let's do it again.
Drug 2.
Okay, 2 is the winner, pretty clearly. This patient lived. New patient. Let's go again.
2.
So I think 2 was the winner again. 2 lived. Again?
2.
2, okay. Live.
2.
Okay. Again?
2.
All right, now we're just going to do a yes or no vote. Who wants to do 2 for the rest of the game? Raise your hand.
2 until they die.
2 until they die. Okay, let's go with that strategy. Let's do 2 until they die. Live. Wow, you guys are good at this. Okay, so you saved 9 out of the 10 patients. And what we can see here is the number of lives saved. The purple is you. That's this line here. And then these other lines, the yellow, light blue, red, and green, those are showing different strategies that we'll actually learn about in today's lecture. And maybe we don't even need to have today's lecture because you guys did better than all of them. So whatever the hell you guys were doing, just keep doing that. Yeah, but for those of us that have to actually think about the math behind this, we should kind of figure out some rationale other than polling the 294-112 class. Although maybe we should add that to the lecture slides for next time. All right, so let's define our bandit, and let's actually think about what optimality means so that we can derive some algorithms and analyze to what degree do they approach the optimal algorithm. So here's the definition. I think all of you already have a pretty decent grasp on this, but just to make it concrete, every time you execute an action AI, you observe a reward from some distribution of rewards, P theta I Ri. So theta I refers to some parameter of the reward distribution for action AI. So for example, if your reward is 0 or 1, like it was in this game that we just played, then theta I can just be a number between 0 and 1, the probability that you'll get a 1 from that action. If your reward is something else, maybe your reward is continuous, then theta I parameterizes that continuous distribution. So theta I determines the distribution, R is a sample from that distribution. And the only thing you know in advance is you have a prior on theta. And maybe if the rewards are 0, 1 like this, maybe your prior on theta is just a uniform prior. But you have some kind of prior, you have some kind of P theta. In general, you might have a prior that's different for every action, but for the sake of simplicity, let's just say you have the same prior for all the actions. So now what you can do is you can actually take this bandit problem and you can define a kind of meta-level partially observed Markov decision process. This is not actually the decision process for playing the game. This is the decision process for learning about the game. So the state in this decision process is actually the parameters of these reward distributions, because this state fully determines the rewards you're going to get. And the belief over that state is your current p hat, your current probability you're assigning to each parameter value. Because you don't know the parameter values in advance, you only have their prior. So each time you observe the reward, you could update your belief about those parameters. If you actually knew the thetas, then this wouldn't be a PUMDP, this would be just an MDP, and this would be your state. Of course, if you just knew the parameter values, then you wouldn't need to reason about how it's an MDP, you would just always pull the best arm. But once you formulate this as a PUMDP, now you can actually do planning through that partially observed Markov decision process. So if you actually solve this partially observed Markov decision process, you would have the optimal exploration strategy. So this partially observed Markov decision process, it actually has known dynamics. The dynamics are just how do you update your beliefs? And you do it in a Bayes optimal way. This is actually kind of overkill though. So while we could formulate the full PUMDP and we could solve it and get the optimal strategy, this is the best strategy you could possibly do with full Bayesian updates, like you literally just use your observations and Bayes rule together with this prior to get your posterior P of theta given all of your past experience. While you could do that, it's kind of overkill. The belief space is a very large space if you have a huge number of arms and so on. So you could do that, that would be kind of the gold standard, but it's overkill and you can actually do very well with much simpler strategies. But when we say Bayes optimal exploration, what we really mean is this overkill thing where you formulate the full partially observed Markov decision process with beliefs about the parameters of these reward distributions. You do correct, fully Bayesian updates to those beliefs, and then you plan for the actions that will maximize your expected long-term reward under those beliefs. So, question?
Are you saying it's overkill because you only need to find the best drug, you don't want to find the probability of the worst drugs?
So the reason I said it's overkill is because you can actually get a strategy that is asymptotically just as good as the Bayes optimal strategy without doing the whole PUMDP thing. So now the statement that I just said, it kind of presupposes something which is a measure of goodness. So before we even talk about which strategy is better or worse, we need to define what we mean by good or bad. So how do we measure the goodness of an exploration algorithm? We use something called regret. So regret refers to the difference between the optimal policy at each time, the difference from the optimal policy at each time step t. So formally, the regret at time step t is capital T times the expectation of the reward of the best action, because that's what the optimal policy would do. The optimal policy would just pull the best arm over and over again. So the expected value of the optimal policy is just capital T times the expected value of the best arm. So that's what the optimal policy would do. And your regret is your difference from that, which is given by the sum of rewards you've seen so far. So if you have the optimal policy already, then your regret should be 0, because in expectation, this minus this should be 0 for the optimal policy. But of course, you can never have the optimal policy right from the start. So achieving a regret of 0 is in general impossible for an exploration algorithm. And it turns out that the asymptotic bound for optimal exploration algorithms is on the order of log of t. So if you can reach log of capital T, then you're in good shape. Then you're within some constant of an optimal exploration algorithm. You cannot do better than that in expectation. Any questions about this? Okay. So this part, this is the expected reward of the best action, and this is the actual reward of the action that you actually took. So your goal in designing exploration algorithms is to minimize this quantity, and the best that you can do is log t. Okay, so how do we do well at this problem? How can we get regrets that approach log t? So it turns out that there are a variety of relatively simple strategies that asymptotically get us log t, or empirically do about as well as those asymptotically optimal strategies. So often you can provide theoretical guarantees on regret, and the guarantee that everybody wants is that log of t. So there are a variety of algorithms that get that up to a constant factor. Their empirical performance, however, even on randomly generated bandit problems, can vary. So there are also some algorithms that I'll discuss that, at least so far, do not have theoretical guarantees, but empirically seem to do as well or better than the theoretically justified methods. And then, of course, for the more complex MDPs, the kind of exploration strategies we use will not have these guarantees at all, but they'll be based on similar principles. So we might hope that at least empirically they'll work well. So that's how things are going to go here. The first class of exploration algorithms I'm going to talk about, and actually probably one of the simplest, is optimistic exploration. So the intuition behind optimistic exploration is that we're going to estimate our distribution over these rewards. There are a few ways we can do it, but if we have just continuous rewards, maybe we keep track of the average reward for each action, which I'm going to denote as mu hat A. And we're going to estimate our uncertainty about that reward. So if you just wanted to exploit, if you just wanted to take the actions that are best right now, of course what you would do is you would take the action for which mu hat A is maximized, because mu hat A is basically your estimate of the expected reward of an action. What you can do is you can construct an optimistic estimate of the reward of an action by taking mu hat A and then adding some estimate of variance or uncertainty, which I'm going to call sigma A for now, times a constant. And the constant basically reflects your optimism. So if you're not sure about what the reward is, well, just assume that it's better than expected. So this is some sort of variance estimate. The intuition behind this is that if you're really sure about the reward for an action, then probably you're going to get mostly mu hat A. But if you're really unsure, maybe you try to play some of those actions which might have a good reward. So you wouldn't play something that has bad reward and you're certain it has bad reward, because then sigma A would be low too. But if sigma A is high, then you might play that action simply because it might be good. So the intuition is you try each arm until you're sure it's not great. So the only time that you would really not do something is if mu hat A is low and sigma A is low, so that the optimistic estimate is low. And then, of course, you have to choose how to calculate the sigma A. And it turns out that you can do really simple things and still get very good exploration algorithms. In fact, you can actually show asymptotically optimal regret even when your estimate of this uncertainty is not even based on rewards at all. It's just based on the number of times you've played that arm. So this is actually a fairly popular class of optimistic exploration techniques, where what you add to mu hat A is just the square root of 2 times the natural log of the number of time steps divided by the number of times you've played that arm. This is very similar to what we saw before for Monte Carlo tree search. In fact, the Monte Carlo tree search rule is based on this principle. So if you analyze this thing, the denominator is the number of times you've picked this action. So if you've picked an action a very, very small number of times, then this value is going to be large. If you've picked that action 0 times, then it has an extremely large value. So the first thing you're going to do is you're going to play each arm at least once. And the numerator, of course, gets bigger the longer you've been playing. So that means that this ratio, you can kind of think of it as roughly trying to estimate of the number of actions you've taken, like how often have you taken this one? So if you've been playing for longer, then you would expect to have taken each action a bit more often. And it turns out that the regret for this, you can analyze this kind of rule, approaches log t. So this is in fact an optimal exploration algorithm, even though it's very, very, very simple. So all you have to do, you don't even need to estimate the variance per se, you just need to keep track of how many times you've played each action. So this is a very simple exploration rule. It works well. The MCTS-based kind of tree exploration is based on this also. And we'll see later on that we can extend this technique to high-dimensional and continuous MDPs with a little bit of tricks to figure out how to calculate this n. So this is a very simple exploration rule that's very important to keep in mind. This is sometimes referred to as UCB, upper confidence bound. Another thing we could do that's a little bit more model-based is probability matching or posterior sampling. This is also sometimes referred to as Thompson sampling. So when we talked about this optimism-based exploration, we weren't really doing very much reasoning about the distributions for these rewards. We just kept track of mu, and then we just kept track of the number of times we picked each arm. We could do something a lot more model-based. We could actually explicitly maintain the belief about the parameters of the reward. So our belief is this joint p hat over theta 1 through theta n. And what we can do is we can then use this belief to explore. So the belief is basically our model of our bandit, and our model is uncertain, because for the arms that we haven't pulled as much, we have a lot less confidence on what their reward distribution parameters are. So there's a very simple idea for how we could explore in this setting. We could simply sample from our belief, which gives us a potential MDP. So our belief is a distribution over what we believe the bandit problem is. When we sample from that distribution, we get an instance of a bandit problem. And then we can just pretend that this model is correct and take the optimal action under this model. So once we've sampled theta 1 through theta n, choosing the optimal action is trivial. You just pick the one with the largest expected reward. So you go and do that, and then you just update your model after having taken that action. So what that means is that if you have some action where the distribution over theta is very broad, occasionally when you sample from the distribution, you'll get an instance of theta 1 through theta n that assigns a very high probability of good rewards to that high variance action. And sometimes when you sample, you'll get a very low probability. So if you sample enough, eventually those high variance actions will get explored because they have some chance of getting thetas that indicate very high reward. And then you repeat. So you can think of this as a very model-based exploration approach. So this is called posterior sampling or Thompson sampling. It's a bit harder to analyze theoretically, but empirically, it can actually be shown to work extremely well. So in some empirical analysis, you can check out this paper called An Empirical Evaluation of Thompson Sampling. It can actually be shown to outperform some of the more theoretically principled methods. And there's a little bit of analysis of techniques of this class, but it's not quite as straightforward as the UCB method. Question?
How is that different from what we did when we learned the dynamics of the problem?
So the question was, how is this different from what we did when we learned the dynamics of the problem? It's actually very similar. In fact, when I talked about uncertainty for model-based RL, it's essentially the same idea. And in fact, doing exploration like this for model-based reinforcement learning can work very well. All right, and the third class of bandit exploration algorithms I'm going to cover, and the last one, is methods that are based on information gain. So these are kind of the most Bayesian of the bunch. These are methods that are actually going to reason about the value of gaining information. So before we talk about exploration and bandits with information gain, let me just introduce the basic principle behind Bayesian experiment design. So in Bayesian experiment design, you want to learn about some latent variable z. So you'd like to figure out what is the value of z. So perhaps z might be the optimal action or the value of the optimal action. Or if you're doing a science experiment, it's like, is your hypothesis true or false? So z is the thing that you want to figure out. And then you might ask, well, which action should I take to learn about z? So the way that you can calculate this in a very kind of information theoretic way is the following. First, we're going to use h of p hat of z to denote the entropy of our estimate of the belief about z. So p hat of z is your current belief about z. Maybe in the beginning it's just your prior belief about z, but once you've gained a little bit of information, maybe you start narrowing down your belief. And h of p hat of z is the entropy. So we talked about entropy before. Entropy basically gives you a measure of how uncertain p hat of z is. So if you know exactly the value of z and p hat of z is just a Dirac delta, then entropy is minimized. If you know nothing about z, meaning that p hat of z is just a uniform distribution, then h of p hat of z is maximized. So it tells you how much do you know about z. And then we can also introduce this conditional entropy, p hat of z given y, which denotes the entropy that you will have about for p hat of z if you observe y. So y is some piece of evidence. Now, you might not actually know that like the particular value of y that you're conditioning on here is the true value of y. So this is kind of this is a hypothetical. It's saying if I observe y, what will be my entropy for p hat of z? So y might be, for example, the reward you observe from pulling some arm. So the lower the entropy, the more precisely you know z. So intuitively, your goal if you're constructing an experiment is to take the action that will give you the observation y that lowers the entropy of p hat of z as much as possible. The trouble is that you, of course, don't know which y you'll observe from taking a particular action, because y is the outcome of your experiment. If you already knew the outcome of the experiment, you wouldn't run that experiment. So the reason that this is a little bit less obvious is that y's themselves are uncertain, and you don't know which y's you'll get. So while you can calculate the entropy of p hat of z given some y that you might get, you don't know which one you'll get. And in fact, you don't want to run the experiment that'll give you a y about which you're certain, because you're already certain about it. So you know, if you're doing like a physics experiment, you wouldn't want to do an experiment to like figure out whether the sky is blue, because you already know that the sky is blue. Like you can just assume that's true and proceed with the next unknown. So you want to do the experiments that'll resolve unknowns, that'll give you values of y's that you're not currently sure about. So what you can do then is you can formulate this thing called information gain. And information gain is a function of two random variables, and it's given by the difference between the entropy of the thing you care about, p hat of z, minus the entropy of the thing you care about given some y. But because you don't know y, you calculate this in expectation over y. So you take your current belief about y, and you compute the expected value of the decrease in entropy for z that you'll get from observing y's according to your current distribution of y's. And in practice, you typically want to compute information gain condition on some action. So your y, if your y is, for example, the reward, then the reward, of course, depends on the action. So written like this, the information gain basically tells you what is the expected value of the decrease in entropy about z, given my current belief about which y's I'll get when I execute action A. And this would actually encourage you to choose actions for which the y's themselves are highly uncertain, because if the y's were very certain, then the entropy decrease would be very small. So let's go through an example now of how we can use information gain to actually construct an exploration algorithm for bandit problems. So this is from a paper by Russo and Van Roy called Learning to Optimize via Information-Directed Sampling. And the particular choice we'll make here is we'll have y be the reward for some action, and z will be the parameter of the reward distribution. So here the game that we're going to play is, can we take actions that maximize our information gain about the reward distributions of those actions? There are other choices we could make for y and z, but these are the ones that they have in this paper that they analyze. So then we'll introduce this quantity called g of a, which is the information gain about the parameters of the reward distribution for a that we expect to get from observing the reward for a when we take action A. So that's going to be the information gain we're going to work with. And then we'll introduce another quantity, which is suboptimality. So suboptimality is the expected value of the reward of the optimal action minus the reward of action A. And all of these expectations and information gains and so on, all of them are calculated using our current belief. So this expectation, of course, it's not the real expected value of the difference between RA star and RA. It's the expected value under our current beliefs, which we update in the usual Bayesian way using Bayes' rule and so on. And then similarly, the information gain is the information gain under our current beliefs.
But the A star is not on the current belief.
So the question is, well, what about A star? Where does that come from? So A star is the action that you believe is optimal under your current beliefs. So you don't know what A star is. So in this case, delta of A is the expected difference between what you think is the optimal action and this action. So the exploration rule that Russo and Van Roy propose here is to take the action which is the argmin of the ratio between the squared suboptimality and G of A. Let's unpack this a little bit. Let's think about what this actually does. So in the denominator, you have G of A, and this is an argmin, which means that if G of A is tiny, then the ratio will be huge, and you will not want to take that action. So that means don't bother taking actions if you won't learn anything from taking them. And in the numerator, you have delta A squared, which means that if suboptimality is very large, then the numerator will be very large, which means that you also won't pick that action. So the numerator just says, don't take actions that you're sure are suboptimal. So gaining information about an action that is really, really bad is probably not worthwhile. So it seems like a little bit of an arbitrary exploration rule, but actually it turns out that if you analyze it, you can also show that this will give you that nice logarithmic regret. So even though it's a bit arbitrary, it actually ends up working well in theory, and also they have some experiments that show it works decently well in practice. Okay, so that's the information gain exploration. Does anyone have any questions about this?
One question is why there is a square?
The question is, why is there a square? The real answer is because it makes their analysis work out. Yeah, so you could imagine that you will just want this, you want to avoid things where this is big. I think the more nuanced answer is that once you start getting negative numbers in there, the analysis gets really tricky. So, okay, so we discussed 3 different exploration rules. They kind of seem maybe a little arbitrary, but also somewhat logical. But let's discuss some of the general themes here. And we'll see these themes emerge again later on when we talk about exploration for more complex decision-making problems. So concretely, the 3 things we covered were optimistic exploration, which is sometimes also referred to as upper confidence bound. So that's where you take the action with the largest expected reward plus some bonus, which is big for actions you haven't taken very much. Thompson sampling or posterior sampling, where you maintain a belief over the parameters of your reward, and then the way that you explore is you sample from that belief, and then you take the action that is optimal for that sample. And then information gain, where you compute the information gain about some variable from some other variable conditional on an action. So for example, you could choose information gain about reward parameters from observing rewards, conditional on the action that will trigger those rewards. And this kind of gives you this Bayesian experiment design flavor. So most of the exploration strategies, and all of the ones that we've discussed so far, require some kind of uncertainty estimation. So the way that you choose how to explore rather than exploit is by reasoning about uncertainty about your beliefs over which actions might be good. Even if sometimes that estimate of uncertainty is extremely naive, like for example in the UCB case, where you just assume that things are more uncertain if you haven't done them very often. You usually assume some kind of value to new information, and this is really essential because if you're going to do anything other than exploiting, you need to believe that there's some value to learning new things, which you can incorporate into your method by assuming that unknown things are good, which is what you do with optimism, assuming that some sample from your belief is potentially a true model, or assuming that just direct information gain is good, which is what happens over here. So these are basically the 2 themes that all these exploration methods have in common, and these 2 themes we'll also see cropping up again and again for the exploration methods we'll discuss next for the high-dimensional problems. Okay, but for now, why should we care about these kind of simple toy bandit settings? Well, first, bandits are a lot easier to analyze and understand. So while we can't really prove very much about exploration algorithms for complex high-dimensional MDPs, we can actually construct proofs for exploration methods for bandit problems, which can give us a good sort of guiding principle for designing new methods. So we can derive foundations for exploration methods and then apply these methods to more complex MDPs where all bets are off, but we have good kind of circumstantial evidence to suppose they might work well. There are a bunch of other things. There's actually quite a bit more analysis we can do with bandits that was not covered in this lecture, but a few things that are maybe worth mentioning. So a very popular class of methods of problems to analyze for exploration algorithms is what are called contextual bandits. We didn't talk about contextual bandits at all, but contextual bandits are essentially bandits where you get a little context vector each time. And these actually have some very practical real-world applications. For example, ad placement can be framed as a contextual bandit problem. You observe the features of a user, and then you pick an ad for that user. Multi-arm bandits don't have a notion of context, but contextual bandits do. And you can think of that context as essentially a state. We didn't talk about optimal exploration for small MDPs, but there is some analysis you can do for sequential decision-making problems, provided they have small tabular state spaces. There's also quite a bit of work on Bayesian model-based reinforcement learning, where you actually do model-based RL and you maintain full beliefs over the entire model, which kind of has a similar flavor to information gain. So if you're interested in more tractable analysis of exploration techniques, these are potentially things that you might want to check out. And also there's quite a bit of analysis for exploration based on Pack-Bayes style formulations, which I really won't go into here because it's quite tangential to the course, but those of you that are more interested in learning theory could check that out. Okay, so at this point, we're going to take a very short break. Let's go for 2 minutes until 11:09, and then I'll resume with a discussion of exploration for complex MDPs.
To ask you, when we did the agent walking, for example, when the agent fell, what was the reward at that point?
This was in like homework 1 or something?
Yeah, but I'm just correlating that to another question. Like I have so I'm building learning process and I don't want it, for example, to fall. So I wanted to avoid this last step. So what's the reward?
So there are a few ways that people actually design these things. I think that the particular setting that's used in a lot of these benchmark tasks is that there actually isn't a negative reward for falling, but the way it's set up is that the episode terminates and you get a small positive reward for not falling. So then you want to like not fall for as long as possible, because if the episode terminates, you stop receiving that reward.
I see. Yeah.
But there are a number of ways that people can have formulated these things in the past. So you could say, okay, there's a big negative reward for the thing that you don't want. You could say that the episode ends and there's a small positive reward for everything else. And these all actually produce slightly different behavior. And perhaps even more frustrating, they all produce different learning dynamics. So for example, you might not want to give a big negative reward, because if you give a big negative reward, then you get big gradients, and if you have a partially trained policy, the parameters of that policy might get a little scrambled.
Yeah, the thing is that in my case, what happens is that you have like something like this, you get 5, and let's say 7, and then you fall here, and let's say you get -1 million.
Yeah.
So next time it learns it should go there, but at the end, because it's gonna end somehow, it will be also minus
Right.
million. So all of the half is.
Well, and this is actually part of why designing reward functions in RL is such a complicated process, because while we might like for it to be purely a matter of specifying a task, in reality it also has a really big effect on the learning process itself. So that there isn't really like a single great answer to it. Unfortunately, there's a little bit of artistry to it.
Yeah, so you're saying just ignore the last step. And
That could be one way to do it, yeah. All right, I think I have to resume the lecture, but I'll be around afterwards. Okay, let's continue. So in the last portion of today's lecture, I'm going to get started on the discussion of exploration algorithms for complex high-dimensional MDPs, and we'll really complete this discussion on Friday. So when we talk about exploration for deep RL, for more complex tasks, we can formulate different classes of exploration methods that are basically going to reflect the classes of exploration methods that we covered when we talked about bandits. So we'll see methods for optimistic exploration, which basically assume that a new state is a good state. So for bandits, a new action was a good action. Here, a new state will be a good state. And this is going to require estimating some kind of visitation frequency or novelty measure. So we'll need to calculate something that tells us how new is this state so that we can determine how good it is. And this is typically done by means of exploration bonuses. So you'll actually give the algorithm a little bit of an additional reward for going to a state that is new and therefore good. We'll talk about methods that are based on the principle of posterior sampling or Thompson sampling. So these algorithms are going to learn a distribution over something. So for bandits, our distribution was over reward parameters. Here, our distribution can be over a variety of things. In model-free RL, good choices would be Q functions or policies. You could also maintain distributions over models and do exploration with model-based RL. And then the way this is going to work, just like with posterior sampling for bandits, is that you'll sample from your distribution. Maybe you'll sample a Q function or you'll sample a policy, and then act according to that sample, pretending as though it was the right one. And then we'll also talk about information gain style algorithms, and this will be on Friday, which try to explicitly reason about information gain now from visiting new states rather than just taking new actions. And here, the actual derivations become computationally very intractable, so there are a bunch of approximations that have to be used based on things like variational inference that we covered before. So that's where that's going to come in. But let's start with the first one. Let's start with optimistic exploration. So as a reminder, in the world of bandits, the optimistic exploration method that we learned about, UCB, you basically pull the arm with the largest expected reward plus a bonus that is big for arms that you've pulled very infrequently, where N of A is small. So you can kind of think of the second term as a bonus assigned to that arm. We basically pretend that its reward is larger than it really is for the sake of exploring underexplored arms. And that's the same principle that we're going to use for deep RL. And I should mention that there are lots of functions that can work for this bonus. So this is the particular one that's analyzed in the paper I had on that previous slide. But basically, you just need some kind of bonus that decreases as N of A gets bigger. So something that decreases as N of A gets bigger, which is big for small N of A and small for big N of A, will do the job. And there have been quite a few choices in the literature with slightly different empirical properties. So how can we use this idea with MDPs? You can execute a particular action, or just the number of times you've been in a particular state. And I'll mostly use the second one, N of S, just to avoid notational clutter, but keep in mind that you can do the same exact thing for N of S comma A. And we'll use this to calculate an exploration bonus. So when we calculate an exploration bonus, that's as though we're doing RL with a modified reward that I'm going to denote R plus, and the modified reward is just the original reward plus your bonus, which is a function of N of S. So just like up here, we had the expected reward of the action plus some bonus. Here we have the expected reward of the state in action plus some bonus. And we're just going to plug these into a standard model-free RL algorithm. So we're not going to worry at all about how our RL is done. We just assume that there exists some RL algorithm, like policy gradient or Q-learning, and we're mainly going to be concerned with how do we calculate this B of N of S. So the function B is just something that decreases as N of S gets bigger. And then we just use R plus with any model-free RL algorithm. This is quite nice because it's a simple addition to any RL algorithm, so you don't have to implement a completely different method to use this. But you have to be a little careful in adjusting this bonus because you do still want your RL algorithm to actually maximize reward. So if you put a really big multiplier on that bonus, if the bonuses are huge, then the algorithm might ignore the reward function. If the bonus is small, then it might not change its behavior very much. So there's a little bit of delicate decision making in how you tune the parameter of that bonus. But ideally, you would choose some class of bonuses that goes to 0 once you've explored enough, so hopefully things will be okay. All right, but there's actually a deeper problem which we have to resolve before we can use this technique. So what's a count, right? When we talked about multi-arm bandits and we had a small finite number of arms, it's pretty easy to just count how many times you've pulled each arm. If you have a small tabular MDP with maybe like 50 states, you can count how many times you've been in each state. But when we're doing deep RL, presumably the reason we're doing deep RL is because we have a really complicated MDP. Maybe we have an MDP that looks like this. So how do you count how many times you've been in each state? Maybe you can say each unique image is a different state, but then there's a very easy answer to how many times you've been in each state. It's either 0 or 1, because you're extremely unlikely to see the same image twice, with exactly the same pixels. So you need to somehow count how many times you've been in each state, but that needs to depend on some salient factors, like maybe you count how many times this guy has been in a particular place, or how many times this thing has been in a particular place, or this thing. So it's not even really about images. Even if we could abstract away all these entities, there's a combinatorially large number of potential configurations that we have to keep track of. So directly counting each unique instance is not going to give us very useful counts because things just don't reoccur very much. We need some kind of softer notion of count, something that actually takes into consideration the similarity between states. And of course, the same, like an even more severe problem happens when we think about continuous problems. So if we think about that robotic hand that we saw before, there you really never see the same state twice because you will never get the same exact values for these like floating point numbers. So here we definitely need some notion of similarity between states in order to use these counts. So we never see the same thing twice, which means we need to put in some kind of approximation for counts. So that approximation is basically going to make use of the fact that some states are more similar to each other than others. So somehow our intuition is that if the skull is in a different spot, but the guy's in the same spot, that's somehow more similar than if both the guy and the skull are in different places.
Questions?
Yes?
I think that it used to be the number of actions. Why here you change it to the number of states?
Yeah, that's a very good question. So the question for those of you that didn't hear is, before when we talked about bandits, we were counting the number of times you took each action. Now we're counting the number of times you've been in each state. The reason for that is that if you assign the exploration bonus based only on the actions, then you're not actually going to incentivize the agent to explore different parts of the environment, because going left, right, up, and down when you're over here has very different outcomes than going left, right, up, and down when you're down here. So you can take into account both states and actions, or in practice you can actually take into account just states, because for a lot of these tasks the number of actions is not that large. Now of course that's somewhat of an artifact of the choice of environment. So you could have a different MDP where the number of actions is humongous, in which case it might be really important to count both states and actions. All right, so how can we understand the similarity between states without having this issue of completely, of never seeing exactly the same state twice? What we're going to do is we're going to fit a density model. We're going to try to estimate P of S. So if S is some continuous quantity, P of S roughly tells us how prevalent that value of S is in our data set. So counting you can think of as the most primitive way to estimate a distribution or density. We can use other ways to estimate densities. So we can fit some kind of density model. I'll talk about the specific choice of density models later, but for now let's just assume that we have some way to fit a function approximator to P of S or P of S comma A. In continuous spaces, maybe it's some kind of, let's say, variational autoencoder style model. In discrete spaces, maybe it's something else. And I'll talk about particular instantiations later. So if you fit a density model and you see a new state that you've never seen before that is very similar to other states you've seen before, your density model might still give it a high density because it's going to generalize. So your model is going to generalize, unlike the counts, which do not generalize. So if your model generalizes a little bit, even if it sees a completely new state, so long as that state is similar, it'll give it a non-zero probability. If it sees a completely new state that is completely different from all the other states, it should still give it a low probability. So what we're going to try to do is we're going to try to use P theta of S to obtain kind of a pseudo count. It's not exactly a count anymore because these are now densities, but we can get something out of it that looks like a count. So here's how we're going to do that. If you have a small MDP and you're doing the conventional counting thing, then the value of P of S can be calculated from the counts. So you can say that P of S is the number of times you've seen S divided by the number of times you've seen everything. So little n is the total number of states you've seen, capital N of S is the number of times you've seen S, and N of S divided by little n gives you the probability of S. So our intuition with pseudo-counts is going to be that a pseudo-count is something that obeys this kind of ratio, but is derived from P of S. So when we're counting, we go from n and little n to P of S. Now we're going to do the opposite. We're going to actually fit P of S using a density estimator and use that to recover big N and little n. Now we have a problem here because we have two unknowns, big N and little n, and only one equation. So we can't recover big N and little n just from P of S. That's not going to work. So we have to introduce one more equation. And the other equation that we introduce is actually very simple. The other equation is what happens after we see S. So if we were counting and we saw the state S, what we would do is we would increment the number of times we've seen S, and we would increment the number of times we've seen everything else. So after you observe a state S, N of S is incremented by 1, and little n is incremented by 1. So we're going to use this as our second equation. So now we have two equations and two unknowns. So we're going to get P of S and this thing that I'm going to call P theta prime of S to obey these equations. So P theta prime of S is the density after you've observed a new state S and updated your density estimator. So let me write out how exactly this is going to work. You're going to fit your density model, P theta of S, to all the states you've seen so far in your buffer D. Then you're going to take some action A, and you're going to observe a state Si. So at time step I, you observe a state Si. And then you're going to refit your density estimator. You're going to construct a new data set that includes Si, and you're going to refit the density estimator, which in practice you might do by taking a small number of gradient steps or something like that. So you're going to improve your density estimator with this updated state added to your data set. And now you're going to use your old density estimator and your new one together to estimate a pseudo count, n hat of S. And then you're going to use that pseudo count to actually compute the bonus. So the bonus will be given by R plus your bonus function, which is a function of n of S. So the way that you're going to calculate n hat of S is by solving that system of equations. So before we saw how we get probabilities from counts. Now we're going to go the other way around. We're going to get counts from probabilities. So the two equations are that before the update, P of Si was n hat divided by little n hat, and afterwards it's n hat plus 1 divided by little n hat plus 1. Two equations, two unknowns. We just solve the equations, and we arrive at this solution. It turns out, like, this is just algebra, but if you solve these equations, you'll see that big N is equal to little n times P of S, and little n is given by this ratio. And this is just a little bit of algebra applied to these two equations. And then you just use big N hat directly. So if P of S is the true probability of seeing S, then big N hat and little n hat will be the true counts. But if you have extremely complex state spaces where P of S needs to generalize a little bit, then you'll actually get counts that take into account some notion of similarity. So then, of course, we have to choose what kind of bonus we're going to use. And there are lots of functions that have actually been proposed in the literature that are basically inspired by optimal methods for exploration for bandits and small MDPs. So for example, the UCB version, the one from the bandit paper that I discussed before, would just be the square root of 2 times the natural log of little n divided by big N. There's a simplified alternative version which also works well, which is just to remove this natural log thing and just do 1 over big N. An alternative is to drop the square root. This is the one that's actually used in the paper that proposed the pseudo counts, but all three of these will do something reasonable in practice. If you drop the square root, then this is actually very similar to just using an estimate of the probability as your bonus, which is kind of reasonable, I guess. Of course, in large or continuous spaces, there's no theoretical analysis for what any of these things do, but for bandits, you can analyze them a little bit. So does this thing work? This is some of the experimental results from this paper called Unifying Count-Based Exploration by Mark Bellamy et al., which discusses the pseudo-count idea. And here what they're comparing is performance on various games using the black is just regular Q-learning. The green is their 1 over square root of n exploration bonus. The red, I don't remember exactly what that is. But you can see that in these cases, basically, if you look at the black versus the green, there's a big gain, especially on the games with very difficult exploration challenges, like Montezuma's Revenge. So actually incentivizing the RL algorithm to visit states with low counts gets it to do a lot better, especially in settings where you have to do a whole bunch of temporally extended things before you observe good outcomes. And what they're visualizing here at the bottom, on the left you see how far you get if you just use regular Q-learning on Montezuma's Revenge. So remember, it's a Mayan pyramid, so you start off at the top, and with regular Q-learning, you sometimes go into the room on the left. If you use exploration bonuses, then you actually cover a substantial portion of the pyramid, so there's a lot more variety in the states that you're visiting. Okay, so that's optimistic exploration. That's basically the deep RL equivalent of UCB. Does anybody have any questions about this method?
Can you just roll out more steps? multi-step, say. I think you just roll out one step to calculate the new P theta, P prime.
Right, so the question was, could it make sense, for example, to update P theta of S not after one step, but after some number of steps? So just like with Q-learning, where you can interleave the different updates to various degrees, for example, with Q-learning you can collect like 1,000 states and then update the Q function for 1,000 gradient steps, or you can collect one step and update once. Here too, you can interleave these updates however you want. In fact, you can derive a batch mode version of this algorithm where you take maybe n steps over here, compute the update in batch mode, and then assign the reward bonuses, and that's perfectly fine too. So if you, for example, this is what you would do is if you have a policy gradient version of count-based exploration. For the policy gradient version, you would of course generate multiple rollouts, then you would assign reward bonuses to all those rollouts in batch, and then you would update your function approximator for P theta of S in batch. Or you can do the online thing kind of like this. So that's kind of a design choice. And of course there's trade-offs, because if you do it in batch, then you can update your density estimator for a lot more gradient steps. If you do the online thing, you either need a density estimator that can be updated analytically, which is actually what these guys used, or if you have a gradient estimator that requires, if you have a density estimator that requires gradient-based updates, then you have to take a small number of steps. But if you take a small number of steps, then of course P theta prime is not actually a very good estimate of the density. So what these guys actually did is they used a more tractable class of density estimators that doesn't require gradient updates. So what I think I'll probably do at this point is I'll stop here, and then on Friday I'll discuss particular choices for density estimators, as well as algorithms based on posterior sampling and based on information gain. So I'll see you all on Friday.